welcome to Ready to Derive. In case you were starting to think, based on your experience with limits, that calculus was invented just so your teachers could give you hard problem sets and grueling exams, think again. As the saying goes, necessity is the mother of invention, and never was this more true than with the invention of calculus back in the 17th century to answer very pressing questions in the realm of scientific inquiry. The story of its creation, independently by two great mathematicians, Isaac Newton and Gottfried Wilhelm Leibniz, is a fascinating one which you should check out. One of those pressing questions was how to find the instantaneous rate of change of an object in motion, whether that be an apple falling to the ground or a planet moving in its elliptic orbit. In this video, we get to see how the powerful concept of a limit enables us to calculate this quantity exactly. Without further ado, let's get started.
So let's kickstart this video with reviewing a scenario from an overview of calculus, my very first video in the calculus series. You leave your house by car to visit family. 4 hours later, you arrive at your destination, a distance of 200 miles away. Make a sketch of your distance from home over time. And this is a problem I give to my calculus students on the first day of class. So the most common journey I see, if we put distance on the y-axis, time on the x, the most common journey the students give me is this. So in 4 hours, you reach your distance of 200 miles away. And I asked somebody to describe that journey, and they're like, well, I sort of went at a constant speed the whole time. I'm like, well, how do you know that? Well, because it's a straight line. And then, so how exactly did you go at a constant speed? And then they suddenly realize, well, it's not very realistic because I kind of shot out of my driveway, got up to speed instantly, maintained that speed, didn't slow down, stop for anything, lights, pedestrians, and then I arrived at my destination right here and just stopped dead at this point, going from a certain speed to 0 in no time at all. So I asked, okay, can we improve on this? Can we make something a little more realistic? And I get all sorts of different things, but everyone suddenly realizes that you got to have a little more curvature in there to be realistic. Let's see if we understand why this is a little better, little improvement. So in this case, and this is what we came to understand, is that even though we don't know the slope for sure because it's a curve, we know that we are starting off out of our driveway slowly, speeding up. Maybe we get onto the highway and we're going maximum speed about there, and then we start to slow down. Again, we don't stop at all, but at least the motion is continuous and kind of smooth. So the question I ask then is, what is your speed at the 1 hour mark? And if you come into the first diagram, then the speed at the 1 hour mark is very easy to work out because you know that your overall speed, let's see, you traveled 200 miles in 4 hours, and that works out to be 50 miles an hour. So your speed at this point here is the same, 50 miles an hour. But what is your speed at the 1 hour mark in the other scenario? Now this is where it gets a little trickier because we need to know kind of how steep the curve is at that point. And that line that I'm drawing there, if you recall, was the tangent line. And we need to be able to work out the slope of that tangent line to get our speed at that point. Well, the thing is, the tangent line only passes through one point, and we don't know how to find the slope of a line using only one point. That's where limits came in. So the whole unit on limits was leading up to this very important moment, as I'll show you on the next slide. So let's move to another scenario. Here we have a ball thrown up in the air with an initial velocity of 60 feet per second. And the ball's height in feet after x seconds can be given by the following function, which models the motion of the ball. This is from physics. And let's just have a look at that function so you can see that the ball is being thrown up, and then up here it reaches its maximum height, and then it just falls back to the ground. So the question that only calculus can answer: what is the velocity of the ball when, say, x equals 1 second? So I'm using velocity here, not speed, because obviously direction matters because the ball does go back down to the ground. So at 1 second, what is going to give us the velocity of the ball? And we know that it is going to be the slope of the tangent line. Once again, the problem is that tangent line only passes through one point. So the most important takeaway from this slide is that the slope of the tangent line If we could just work that out, that would give us the instantaneous velocity of the ball at that particular moment. So let's do this little workaround. Here's the graph of the height of the ball with time, and our desired goal is to find the slope of that black line, the tangent line, which will represent the instantaneous velocity at t equals 1 second. So our workaround is to find the average velocity, because we can find that over any interval just using the slope formula. I'm going to pick the interval from 1 to 2. So I am picking this interval between 1 and 2, and see what happens over that interval. So what I'm actually looking to do is find the slope of that line, the blue line, which is called the secant line, and that will give me the average velocity. So the average velocity is just the change in height over the change in time. And we could read off the height of each of these points at t equals 1 second, but it's not very precise. And at t equals 2 seconds, which looks like it's over here. Not very precise, but it could work. However, recall we do actually have an equation for this function. So we can use that equation to find the change of height over change in time. Notice that now that we have the equation, this y value will just be f of 2. And this y value will be whatever f of 1 is. So let's work those out. So we take 2 and we plug it in for x in our function. And we find that the height at 2 seconds of the ball is 56 feet. And we repeat for 1 second. And we find that the height after 1 second, that would work out to be 44 feet. So now the average velocity we can just get by doing change of y over change of x. Well, I'm going to put that sort of more formally first. So it's really f of 2 minus f of 1 divided by 2 minus 1. And then I'll put the numbers in. That's 56 minus 44 over 1, which works out to be 12 feet per second. So the slope of this secant line here is 12 feet per second. And sort of the takeaway then, the slope of the secant line, if we can find that, that'll give us the average velocity over an interval. Now notice it doesn't really help. It doesn't seem like a very good approximation of the slope of the tangent line. We know that it's steeper, so we know we're going more than 12 feet per second, but it's still not very accurate. So we are going to improve this estimate in the next slide, and you can probably predict that we'll do it by taking smaller and smaller intervals. So let's improve the workaround by finding the average velocity of the ball over progressively smaller intervals. So we already calculated it over the interval 1 to 2. The average velocity is 12 feet per second. And now we're going to repeat for the other 2 intervals. So I'm calling up that average velocity formula, the slope formula in disguise. And we're not going to do the calculations on this page. I'll leave it up to you, but I'll just show you the general format. So to work out the average velocity over 1 to 1.5, this interval, we would find f of 1.5 again, the height of the ball at 1.5 seconds, subtract the height of the ball at 1 second, and then find the time difference, that's a half a second, has elapsed. And if you work that out, I'll leave that up to you, it should come out to 20 feet per second. So hopefully that's a little more accurate, but let's improve. In this case here, we were actually looking at this time interval. That's a very small time interval. Feels like that would get very precise. So once again, you put 1.001 in here, then 1, 1.001 here, and 1. That's a very tiny time interval, fraction of a second. And if you work that out, that comes out to be 27.98 feet per second. And so you could repeat that over and over again and feel like you could get pretty precise. So let's look at the 3 scenarios. So we know that we worked out from the slide before that this was 12 feet per second. And the green looks like a little more accurate, 20 feet per second, average velocity. And then the purple, 27.98 feet per second. And now if we look at, let's bring the tangent line back in. Well, that looks very, very close to 27.98. So I'm sort of going to wage that perhaps if we went from the interval 1 to 1, which of course is just really at the time x equals 1, I'm thinking that it's looking so close to 27.98 and that just rounds up. So maybe it's 28 feet per second. It's hard to imagine it being any more than that. So let's go to the next slide and see if we can confirm. So it's on this slide that the magic of calculus is about to happen. Limits to the rescue. We're going to get clever here and find the average velocity of the ball over an interval from 1 to, well, what's that? 1 plus h? Think of h as a little bit, a tiny little amount. So in the last slide, we made h 0.001. It's pretty precise. If we could make h as small as possible, that would be very helpful. So the average velocity, as we know, is given by this formula, change in y over change in x. And in this case, we know that we have to, sort of the later time period is the 1 plus h minus f of 1 over 1 plus h minus 1. And we can already see that when we subtract 1 from 1 plus h, we're going to be left with h. So now we just need to work on the top part. So in this case, let's look at f of 1. So if we put 1 in here, we would do 60. Let's do this one's easier. Just put 1 in there, and this would come out to be 44 feet. We found that in the previous slide. So this part here, finding f of 1 plus h, is a little more involved because now we're just going to end up with an expression in terms of h. So let's just start distributing and simplifying. So the first thing we would get is 60 plus 60h minus 16. And then now for 1 plus h squared, be sure to multiply out correctly. And it would be this expression. And so now let's distribute the 16. Get minus 16 minus 32h and then minus 16h squared. And as a last step, let's just simplify where we can. So it looks like 60 and minus 16, that's going to be 44. 60h minus 32h is 28h, and then we still have the minus 16h squared. So we have now everything that we need to put together the average velocity formula. So the average velocity formula, remember we had to take f of, let me use different colors here. So we have to do f of 1 plus h first. So f of 1 plus h is this. So let's put that in. So it's 44 plus 28h minus 16h squared. And then we have to subtract f of 1. So f of 1 is here, which is 44. So we'll just do minus 44. And we mustn't forget that on the bottom, we discovered up here that we're going to be left with h. And let's simplify in the top. Look, the 44's cancel. We get left with 28h minus 16h squared all over h. Oh, and how convenient. The h's cancel, and we're left with this. Now, how is this going to help us to find the instantaneous velocity? Well, there's only one thing that we need to make happen here. Remember that h was just a little bit? Well, ideally, h would just be 0. Well, now we're at a stage where we could actually put in h equals 0 here legally and get an answer. So all we need to get the instantaneous velocity is we need to take the average velocity and just make h go to 0. Hence, we need our favorite concept thus far in calculus, the limit. And the limit of this as h goes to 0, well, that's completely legal. I can just plug in 0 for h, and I get left with 28 feet per second, which is what we predicted in the previous slide. Look at us go. So we're going to regroup and kind of formalize what we just did in the last slide and come up with a couple of definitions which are very important as we move forward in calculus. So we worked out the average rate of change over the interval 1 to 1 plus h, but now we want to keep it general. What about for any value a to a plus h? This is what will help us to develop a formula. So let's get a sketch of our function. So this is f of x here, and let's indicate a and a plus h. So we'll make this a And we'll move a little further along. Remember, h is just supposed to be a little bit, but we've spaced it out here so we have room to draw. And the average rate of change over that interval, well, how do we calculate that? That is just the slope of the secant line. And we have the general formula, rise over run, so delta y, rise over run. And the change in y is just on the numerator, and the change in x, or the run, is the difference between these two, which is just h. And let me just call this point P and this point Q. This is this expression we just wrote is called often referred to as a difference quotient, because in the numerator we have a difference of two values. What two values in particular? Well, you can see that f of a is just the y-coordinate of the point P, and f of a plus h is just the y-coordinate of Q. So it's a difference of the two y values, and h is the difference of the two x values. So let's recall that our end goal is to find the slope of the tangent line at P, or the instantaneous rate of change. So how could we use the formula for average rate of change to create a formula for the instantaneous rate of change? Well, if we recall before, what we did is we just thought about, well, what about if we just move Q closer and closer to P? So you could imagine if we moved Q into that last position, that secant line is looking a lot better as an estimate of the tangent line. And how would we affect this? Well, the only way that Q is going to move closer and closer is if we let h get smaller and smaller, hopefully approaching 0. And that should be a familiar idea, because in that point all we need to do is stick a limit statement in front of the average rate of change formula and say, what is the limit of this expression as h tends to 0? Now notice we have a slight change in notation from delta y over delta x to what we say here is dy over dx. In fact, we refer to that as dy by dx. And that is also a kind of, I like this notation because it sort of gets at the idea of slope. Although this is not really the slope you could calculate directly, you could imagine it as being representing, if you had the world's smallest right triangle and you had a very tiny change in x, what would be, that's dx, what would be the resulting change in y? So it's sort of rise over run, but obviously you don't calculate it by measurement. And so it's not actually a ratio, it's just notation to represent the instantaneous rate of change at x equals a. So as if there wasn't already enough to kind of comprehend, I'm going to introduce an alternative definition of the instantaneous rate of change. It's really not any different from the one before, just the notation is different. So don't be overwhelmed. It's going to generate a formula which is sometimes a little easier to use. So once again, we have our function f of x, and let's call this point A. So A here. And then instead of representing the increment as A and then A plus h, we're just going to call this x. Because why not? We could call it whatever we liked. And then if we do that, then you realize that, of course, this position, the y-coordinate here, is still going to be f of a, but the y-coordinate that corresponds to, let's just call this p and q again, the y-coordinate that corresponds to q is just going to be f of x this time. And so the formula for the slope of that secant line is much the same, except that instead of f of a plus h, we have just f of x minus f of a. And on the bottom, notice we have just x minus a, which is the run. So that doesn't simplify to h anymore, but it's still the same idea. And so to estimate, or to actually evaluate the slope of the tangent line or the instantaneous rate of change, we just stick another limit statement. Notice again, though, let's highlight the differences, that instead of h going to 0, there is no h, so it's a limit as x approaches a. As x approaches a is really the same thing as what we said before as h approaches 0. It achieves the same effect. As x approaches a, q moves closer and closer along the curve to p, towards p, and eventually lands right on p to give us the slope of the curve at that point. So let's do a little practice using the alternative definition, the alternative formula for the instantaneous velocity. When we found it for x equals 1 second, the instantaneous velocity, we use the previous formula, so it's good to practice both. And let's make the sort of the easy substitution right now is that a, in this case, we want it at when the time is 2 seconds. So we can just replace at least this much, replace a with 2. Now you're not necessarily going to like the algebra involved in this problem because there's some factoring that takes place, but sometimes this second formula is really much more expedient to use. So while we're at it, let's just work out f of 2. So we just plug 2 in for x, and you can work out that that comes out to be 56 feet. So at 2 seconds, the ball is at a height of 56 feet. And then we just replace in the formula. So f of x is, well, that's just the function itself. So we are replacing for f of x first. And then for f of 2, we just work that out. That's 56. And we have x minus 2 on the bottom. Well, you could think to yourself, well, why couldn't I just plug in 2 right now? If you tried to plug in x equals 2 into this, you would get 0 over 0, which would be indeterminate. So we have a little algebra manipulation to do here in order to be able to plug in x equals 2. Well, if you rearrange the numerator so that it's in decreasing order of degree, let's see. So we're much more used to be able to factor. We see we have a quadratic, and it's easier to factor if we have the leading term being the x squared. But it's a little hard with negatives in front. So we're going to factor out negative, the common factor, which is -4. And if you pause a moment and just do that yourself, you should find out that it comes to this, 4x squared minus 15x plus 14 all over x minus 2. And now the magic of calculus is about to unfold once again, miraculously. Well, we know that x minus 2 is the bad factor in the bottom because we can't plug in x equals 2. So this must factor into something times x minus 2. So I'm predicting that, but you could just go ahead and you could just take this and factor this, and you would find that what goes in here is, well, let's put that in blue, is 4. This becomes 4x minus 7. How convenient. The x minus 2's cancel, no longer making it illegal to plug in x equals 2. So I get left with this, 4x minus 7. And if I plug in 2 into that, it comes out to be -4. So miraculously, the instantaneous velocity of the ball at t equals 2 seconds, we discover it's -4 feet per second. In this last slide, we're going to see what we have achieved so far and preview what's coming next. So we began by finding the instantaneous velocity of the ball at 1 second, and we found that to be 28 feet per second using the first formula. And then we were asked to find it at 2 seconds, and we found that to be -4 feet per second using the second formula. So what if I asked you to find the instantaneous velocity at 3 seconds? You'd probably be getting a bit frustrated now, feeling like you're doing a lot of algebra, the same algebra over and over and over again, but to no avail. So let's just have a look, sort of go through what you would do. We're not going to go through all the motions again. What you would do to find the velocity at 3 is, using the first method, you would do f of 3 plus h minus f of 3, if you recall, and find the limit of that as h goes to 0. And if you were to do that, you would have to plug it 3 plus h into the formula. That means you have to do some foiling, expanding, simplifying, tedious sort of stuff. Well, okay, so we could say, well, what about the other formula? What if you used the second formula? So we would, in this case, we'd plug in f of x minus f of 3 over x minus 3, and that feels a little better because it would be 60x minus 16x squared. But if you recall, then we get into some factoring, and the factoring of a quadratic whose leading term is not 1, that's kind of tedious as well. So you might ask to find the velocity, at 3, instead of going through all the motions all over again, because what if I then wanted the velocity of the ball when it hit the ground, right? So down here, what would be the velocity? Well, there must be a better way. We're repeating the same steps over and over again. There must be a formula we can derive that we can then plug in the value of x at any time and then work out the velocity at that time. And that's what's coming in the next video.
And that brings us to the end of this lesson. I hope you found it helpful. And if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.